Continuing on with the Mark II series, we're taking a look at the rockets today. You know, the blades, they were kind of more of a purely mechanical system. Rockets themselves, there's a lot more to be considered. You have to worry about the dynamics of flight, you have to worry about the launching mechanism, you have to worry about containment, you have to worry about safety. There's a lot more that can go wrong with the rocket system. So this is a far more complex system in my opinion than kind of the other ones I've worked on. This is gonna be kind of a two-part segment. We're gonna have today's video, lead up, and then we're gonna have the part two, which is gonna be an even more technical deep dive into combining all of the subsystems that we want together, and then also potentially proposing a future design that kind of improves on that. So look out for that one. That one's gonna be fun too. But today we're taking a look at the kind of comprehensive overview of what's led us up to where we are now. So I always like to talk about the inspiration behind kind of what got me the system. And I feel like this is a pretty easy one to guess. Iron Man 1, 2008, the Mark III. His suit has wrist rockets. Boom. We're taking that as our base inspiration for this. We got wrist rockets and we're implementing them. The Mark II rockets have 4 core subsystems. They have our containment, our ignition, our stabilization, and our sensing. Those systems all combine nicely to get a rocket to fly straight. In order for it to be really an advanced system that has Iron Man kind of vibes to it, we want it to be hitting our target when we launch it, and it needs to have some sort of way to keep its path during flight. When you look at rockets in a broad scale, a lot of that can be achieved through fins, which provide your classic kind of stabilization during flight. But also you might have seen sometimes rocket engines use gimbals to actually adjust thrust vectors and keep the rocket stable. We're gonna be looking at the first iteration of the rockets for the Mark II. And that was a very basic design. It was really just designing a basic rocket frame that had twisted fins to kind of get that potential gyroscopic stabilization during flight. That gets me like basically 85% of the way there. I can shoot my rocket and I can ignite it electrically, but you know, it's not gonna fly straight, as you can see. 2, 1. You can imagine taking the fin design of the rockets and really engineering and kind of hammering down the science would probably get me further in terms of linear stabilization. However, fins themselves, they take away a small part of the energy from the rocket's flight, and that's going to be my excuse for not optimizing the fins. Part of the force vectors from the air flowing over the fins actually provides a tangential force to the rocket, imparting a spin. However, for the size of my rocket, you know, the cumulative surface area of the fins would need to be so large that it's probably going to start taking away a significant portion of the actual thrust vector that I'd want, and a lot of that actually is going to be converted into the rotational velocity of the rocket as it flies. Ideally, we want all the thrust to be going into getting the rocket to fly as far as possible. That system was very basic. It was really just the rocket in the frame of the suit. I had the igniter in the back and I'd launch it. The main thing that came from that was the exhaust port, which hasn't changed at all. Essentially, that just allows me to redirect the exhaust of the rocket out of the forearm and away from me, and also away from the plastic, because since it's currently plastic right now, you can imagine that's gonna melt with high temperatures like a rocket exhaust. This was almost more like a proof of concept kind of thing. Can I fit a rocket in the arm and can I launch it and get a cool effect? And yes, but I don't get the linear motion that I want. So now we have to kind of start redesigning and rethinking our rotational stabilization mechanism. Kind of thinking, you know, what systems are used to gyroscopically stabilize a rocket during flight? You know, we already got rid of fins, we can't do that. There's potentially rifling in the barrel, which essentially just guides the bullet to spin really fast as it goes out the barrel. That helps stabilization, that takes away energy from flight as well. But also you can think that some of these systems, they have redirected exhaust ports that angle the thrust vector in such a way that it provides a little bit of a tangential force to the rocket as it flies so that it spins. But since you're also using the thrust to stabilize the rocket and launch the rocket, you're taking some of that energy and putting it into the rotational velocity. So we don't want that either. You know, we want something that isolates the thrust from stabilization and just uses the thrust purely for flight. That is kind of where this next design goes. This one kind of started playing more with very high energy density systems. So thinking back to pneumatics, which is a theme that comes up quite a bit in these videos, is using a pneumatic high pressure airflow on the rocket to get it to spin really fast in the barrel and fly straight. I redesigned the rocket to have these little pockets that were patterned along the circumference. So it almost acted kind of like a water wheel, but for air. And that essentially forces the air to be directed into those pockets, and those pockets create a tangential force to the rocket that get it to spin really fast. A lot of the problems that I've had with pneumatics in the past is that pneumatic systems themselves require a large amount of heavy duty components in order to make them operate properly. So I started thinking about more low profile pneumatic systems that are out there, and maybe thinking like an airsoft gun has a CO2 cartridge that's very high energy density and it's very small. So I was thinking about using a CO2 cartridge as my pneumatic storage to get the rocket to spin up. With the pneumatic system, I was kind of able to validate my hypothesis of if I spin the rocket really fast in the barrel and then I launch it, it's gonna fly straight. And it works great. I was able to inject the high pressure air from the CO2 cartridge onto the rocket in order to get it to spin really fast, and I was able to launch it and it flew straight. That was perfect. However, for the test that I did, it was very manual. There wasn't a lot of electrical control. I was using a ball valve to release the gas, and I was using a button to set off the igniter. My next step from there was to actually try and make everything electrically controlled. Since I need to use a solenoid and electrical valve, those need to be a lot beefier in order to handle the high pressure air from a CO2 cartridge. So when I switched to a solenoid, I ran into the problem that the pressure from the CO2 cartridge was making the solenoid bind, which prevents it from retracting. And then also looking on the ignition side for the system, I was still using the same igniters that came with the engine, and I was kind of placing them inside the back of the rocket and spinning the rocket really fast around them, and it was almost like floating in there. And when it would get hot, it would ignite the rocket because it was still in close proximity to the little black powder charge that's in the back of the rocket. So that still worked for this system, but it's gonna not end up working for us in the future. At least we know that inducing a high speed rotational velocity into the rocket before launching works for stabilization. We just have to find another way to do it without high pressure air. Taking that idea, I decided to use a brushless DC motor to actually impart a very high spin onto my rocket. However, it's not that straightforward. One of the ideas I tried out was using like a roller, having a shaft connected to the motor, and that shaft has a kind of rubber wheel on the end. And that wheel has a high friction coefficient, so when you put it on something, it's gonna potentially move it. And if that thing is a rocket, it's gonna make the rocket spin fast. However, because it has a high friction coefficient, you can imagine when the rocket tries to leave the barrel, that friction is gonna require some sort of energy to break through it, and that's gonna take away from our thrust. So we want something that's able to spin our rocket, but also disengage very easily. I thought about using a gear connected to the motor, and that gear meshes with the gear on the rocket, and then when that motor spins, it interacts with the gear on the rocket spins, and then when the rocket launches, since the gear teeth are like this, it just demeshes and it flies, and it doesn't lose as much energy to release itself than it would if it was like a friction wheel. So that's where we are now for the stabilization mechanism. That is what we're trying to get to work. It's worked on multiple occasions independently. I've yet to launch it with that mechanism actually in function, and I've tested all the other systems separately as well. Also, a side note on this gear train mechanism, which is why it's been such a pain to do, is that since I have the motor to control the side blades kind of in the path where the rocket is, and the brushless motor behind that, I have to go around it with the drivetrain from the motor, and that adds levels of complexity, and it's a whole thing. But it's kind of led us to some cool designs in that area. Part of the design requires that I have a gear coming out of the motor. So using just an off-the-shelf brushless motor, I don't really get as easily of a mounting point for a gear, unless I do a lot of custom design myself. The drivetrain has gone through a lot of designs on the output gear from the motor, and then also a lot of designs from the actual gear train that transfers to the rocket, but it needs to work with all the other subsystems. And in that process of trying to get everything to work together, there's been some changes for everything else as well. So you can imagine that the ignition, kind of having the igniter planted in the back of the rocket, isn't gonna hold up over time. When I have a kind of enclosed system, I need to be able to ensure that my igniter position is constant and it doesn't waver. Because if the rocket spins really fast and the igniter moves in there and it kind of breaks or something because it's very fragile, then I can't ignite my rocket. So we need something that's robust. I started thinking about arc lighters, embedding some arc lighters in the back of the rocket. Then I kind of ran into the same problem there, where like the rotating rocket spinning really fast kind of disrupted the arcs and kind of prevented them from properly igniting the rocket. I was able to get the arc lighters to work once, but it was when it wasn't spinning. So then I started thinking about igniters that aren't necessarily embedded in the back of the rocket, but something that's more of an external force that can somehow ignite it. So I started thinking about using a laser. So a very high power laser focused on the inside of the rocket should ignite it and get it to fly straight without having to worry about the rotational speed or any of that disrupting how well the igniter performs. So I tested that system by using a kind of a lower power green laser. All I did was turn it on and tested to see if it would actually ignite the rocket and set it off, and it did. However, the exhaust plume from the rocket went through the tiny channel that I made for the laser to go through, and then it destroyed my laser lens. So now I need to have some sort of protection mechanism for the laser. I just designed these polycarbonate kind of inserts that just protect the laser from the actual exhaust. So we still get, a transparent window to go through, but something that's okay if it gets destroyed by the rocket exhaust. We know our laser works, and then I bought a new one that's a high power blue laser, and that's what we're gonna test next. So at the very beginning, I also mentioned containment. So containment, the main thing there is just having something that keeps the rocket inside the barrel at all orientations of motion, right? If I just have an exposed barrel, the rocket's gonna slide out if I go downwards. I need something to keep the rocket in place, and especially now I need something to keep it meshing with the gear from the drivetrain. So with that in mind, Iron Man, he uses these kind of exposable rockets, these things that pop out like that. I don't have the room for that type of a system, so I thought maybe more of a flap that opens up and down would be better for that. That's what I've been using for this system as well, and that also works on its own independently and through the Mark II Wi-Fi network. The rocket flap works, it moves up and down and allows me to release the rocket when I want to, but now I want to include that into the final test and make sure everything works together. So there was a bit of a design challenge as well for the rocket flap. The main thing was trying to find space for the motor driver. I ended up doing kind of a fun electrical engineering challenge where I split the motor driver in two and designed a flexible cable that connects them top and bottom, and then allows me to almost flip the driver on itself, kind of like a U shape, so that I can keep it very compact and kind of keep it in the area that the rockets are, so that I don't have to worry about relocating it somewhere else and dealing with all those wires. I just have the motor driver where it's supposed to be, right by the rocket and right by the motor. and it kind of stays with the system. And then another thing that's also pretty important for this is going to be the actual sensing. So with the brushless DC motor, there's a lot of ways you can actually get positional data from the motor. You can have an encoder, classic. You can have Hall effect sensors embedded in the motor that read the electromagnetic field being generated when the motor spins to get like position data. Those require taking up space at the motor location. I mean, you know me, I like to relocate my sensors and kind of put them all around the suit so that they're not necessarily on the motor, because that's too easy. You know, we like to mess around a bit. So my thing was also using some sort of kind of relocated sensing mechanisms for all the motors being used for the rockets. We have two main motors. We have one that spins the rocket really fast, and we basically need to track how fast the rocket's spinning. And we also have the motor that controls the flap, and we need to track the position of that motor. So starting off with the low-hanging fruit, to actually track the position of the flap, I just use two Hall effect sensors, one on the top of the motion and one on the bottom, put magnets on the flap, boom, boom. We're able to track the motion of our flap. Works great. You know, same method I'm using for the side blades, nothing crazy there. However, we need to also measure the rotational velocity of the high-speed brushless motor. And that's a pain because I'm not using any sort of traditional sensing mechanisms. And the most important part of that is really the rotational speed of the rocket. Who cares what's happening at the motor side? If the rocket isn't spinning, that's a problem. So I decided to use kind of external sensing mechanisms for the rocket, and I thought about a tachometer, which uses infrared light and infrared reflectors to kind of read the amount of times that you see a reflection from the indicator. With that in mind, I decided to design an infrared transmitter and receiver board that essentially transmits infrared light into this small channel that can see the rocket, and there's little indicators on the rocket that reflect the infrared light back when the rocket kind of lines up with the light from the infrared sensor. And then when it reflects it back to the receiver, that gives me a little bit of a signal on the microcontroller side, which I can then use to process and actually get a rotational velocity from the rocket. And that'll tell me when I need to launch the rocket. Because the rocket isn't spinning fast enough, we know it's not gonna fly straight. So instead of tracking the motor, because there could be some losses in the transmission, it makes sense to track the rocket because that's exactly what we need to know how fast it's spinning. So that's the overview of like literally everything that's being embedded into this process. All these subsystems have been kind of improved over time to kind of work together a lot better. But now we're getting to the point where we can finally test them all together. And then, not only when I get this working, y'all are gonna get kind of the next preview into the future design. Because I'm just trying to get this to work now. At this point, it's like I've sunk so much time into trying to get this current state of the system to work that I want it to work before I improve it again, because I don't want to discard all my work and kind of throw it in the dust. And it's about to work too, so we're like pretty close. However, we're gonna take like a deep dive into the math and kind of propose an improvement design that I'm gonna implement soon after we get this one to work. So that one's gonna be fun. That's gonna be real technical, so it's gonna be even more in depth than this one. And then once all this is working and we kind of optimize the designs, then we're gonna get to do a real life test video. We're gonna go outside, I get to put it on, we get to do all the stuff, we combine it with other subsystems, we get to do the full Ironman experience, right? So we're getting there, we're getting close. But yeah, this is getting fun, I'm liking this.